Okay, I'm Damien Bonnet-Eymard, ESR02, and today we'll introduce you to physics-informed neural networks and how they can be used, for example, for material discovery. So imagine you have just discovered a new material that seems to have very promising properties. But of course, before using it in your products, you want to model it, to have some models on how it can behave. And in order to do that, you carry on some experiments, you gather data, and in the end, you have information that range from more theoretical to more data-based. So on the physics part, you can have, for example, partial differential equation, other conservation laws, and then you can have information on the material behavior that you can have using calibration. And on top of that, you can have sensors that gives you measurements about your material, your model. And often the challenging part in modeling this material is to know how to gather all those different information in the same model. And maybe even more challenging is if you want to, if you have a new information, if you want to change, for example, the material behavior, the material model, you may need to update your whole model depending on the architecture that you use. And so a convenient way would be to be able to gather all those constraints in a single model and to be able to add constraints really easily. And that's something you can do actually with physics-informed neural networks. So what's the idea behind that? You want to use a neural network to approximate the physics quantity that you have. And then usually the framework for neural networks is to have a loss that you want to minimize during the training of your neural network. But to add some physics into this model, what you can do with neural networks is actually to calculate the derivatives of the output in regards to the input. And by doing so, you can calculate the partial differential equation, the PDE, of your approximator, of your PDE, of your neural network. And this PDE, you want to minimize it during the training, so you can evaluate it in your domain, wherever you want. You can also do the same with the boundary condition. You evaluate your approximator on the boundary and you compare it with the non-boundary value, the boundary condition. And on top of that, if you have some measurements, you can always also compare the approximator to this ground truth reference. And you want to minimize all those loss terms so that in the end, if you reach convergence, you have a model that is both compliant to the physics, to the boundary condition, and also to the data. And you can also imagine to add some constraints the same way by adding some extra loss terms really easily. And how can it look like for material discovery? So this is a simple showcase example on linear elasticity. You have this boundary value problem with governing equation, boundary condition. You add some measurements inside, and you want to find the material properties. And you can do this pretty efficiently with this kind of framework. So here you can see that in a few minutes, the model managed to recover the solution, the displacement field, but also the material properties, so to solve this inverse ill-posed problem. Thank you for your attention.